Hi everyone. So in this video we're going to continue where we left things off with our truth tables for propositional logic. I kind of left you hanging with this argument here and asked you to write out the complete truth table to test this argument for validity. So let's try to work through this together and see if we can't determine whether or not this argument is valid or invalid. So remember, when we are testing a complex statement for validity, we are looking for our technical definition of validity, which means that arguments are invalid if they have true premises and a false conclusion. So where we left things, I indicated that this is our first premise, premise 1, either not R or S. And this is our second premise, premise 2, not S. And then we have our backdash here, so this indicates our conclusion, not R, right? So what we are going to do is build out the truth tables for every one of our premises and for our conclusion, and kind of run a cross-check to see if we come up with a row where the values are true under the premises column and false under the conclusion column. So in order to do that, we have to fill in our reference columns, right? I left you with this. This is the reference column. And we had to determine how many lines we need on the truth table. And because this is a statement with two variables, R and S, the number of lines has to equal 4, right? Because L equals 2 raised to n, where n equals the number of values, the number of variables. So we're going to build our truth tables by dividing the values for R in half, where the first half are 2. So we have 2 values for R at the beginning of the column, true and true, and then we have 2 values of false, false and false. So lines 3 and 4 are false. And then we have to split these values in half to find the columns for S. So S is true and false. True and false. Very important to write our our reference tables correctly, because that will be sort of our guiding compass as we try to discover the values for every other premise and conclusion. So now we're prepared to discover the values for the first premise. So we have to think for a moment about what the most important part of the statement is. And to me, it's got to be the disjunction, the wedge. This is a disjunction bringing together not R and S. So this premise says either not R or S. So we have to find the values of wedge. So let's do this very methodically and first find the values of not R and not S before proceeding to find the values of wedge. So to find the value of not R, what we simply do is go over to our reference table and negate those values, right? The negation is a negation of the values of R. So on the first row, I see that R is true, so not R on the first row has to be false. On the second row, I see that R is true again, and so not R has to be false. On the third row, I go down and see that R is now false, so not R has to be true. And finally, on the fourth row, I see that the value for R is false, so not R is true. So these are the values for not R: false, false, true, and true, simply negating the values for R on the reference column. Now we find our second disjunct, S, and this one is more straightforward. All we have to do is plug in the values for S on our reference table. So I see on the first row that the value for S is true, so I'm going to write true. Then I see that the second row, S is false, false. And on the third row, S is true, so I write in true. And then on the fourth row, S is false. False. I don't have to alter it at all because it's just the values for S. Okay? So now we have to write in the values for our disjunction, our wedge. So in order to do that, we have to remember our rule, our truth functional rule for disjunction. Disjunctions are false only when both of the disjuncts themselves are false. So as soon as we have one true disjunct, the wedge as a whole is true. It's an either-or statement. So let's do a kind of truth functional analysis here. On the first row, the first disjunct is false, and the second disjunct S is true. So I know that the first row for wedge is true because I have that true S. Okay, I move down to the second row and I see that the value for not R is false and the value for S is false. So on the second row, wedge as a whole is false. Both of my disjuncts are false. Okay, so on the third row, I see that not R is true and I see that S is true. So disjunction on the third row must be true. Now in the fourth row, not R is true and S is false. So wedge as a whole is false. Is true. So wedge is only false on the second row where I have two false disjuncts. All right, so these are the values of the disjunction as a whole in premise 1. Okay, I now move forward and have a look at the values for premise 2, which are not S. So in order to find not S, I simply have to go over to my values for S on the reference column and negate them. So whatever the opposite value is, I plug that in. So on the first row, S is true, so not S on the first row must be false. On the second row, I see under the reference column that S is false, so not S must be true. On the third row, I see that S is true, so not S must be false. And in the fourth row, I see that S is false, so not S must be true. So we've inverted the values so that not S reads false, true, false, true. All right, so these are the values for premise 2. And now I have to find the values for our conclusion, not R. So to find the values for not R, I go back to our reference column. And even though we've written it out here in premise 1, I think we should write it out again so that we have a complete set here. So we're going to negate the values for R in our reference column. So I see that R in the first row is true, so not R has to be false. On the second row, R is true again, so not R has to be false. And then on the third row, R is true, R is false, so not R has to be true. And on the fourth row, R is false, so not R has to be true. So these are the values for our conclusion. Not R is false, false, true, and true. Now what we have to do to check for validity is to kind of cross-examine all of the values for our premises against our conclusion to see if there's an instance where we have true premises and a false conclusion. So let's have a look at our first row. Premise 1 is true, premise 2 is false, and the conclusion is false. This is actually valid, even though we have some false values in there. So the first row checks out and is valid because we don't have an instance where there are true premises and a false conclusion. That's what we're looking for. Now let's look at the second row. Premise 1 is false, premise 2 is true, and the conclusion is false. Again, this one checks out. This is fine. We don't have a case where we have true premises and a false conclusion, even though premise 1 is false and the conclusion is false. So be careful with that. We're not just looking for false values. We're looking for a specific arrangement where true premises are generating a false conclusion. Now in the third row, we have, for premise 1, a true premise. Premise 2 is false, and then the conclusion is true. So this one checks out. We don't have an instance of true premises and a false conclusion. So far, so good. And finally, I see that premise 1 is true, premise 2 is true, and the conclusion is true. So the final row 4, checks out. We have all true values. So this argument is valid. We have not violated the rule. We don't have a row where we have true premises and a false conclusion. So this is what we're looking for. If we were to have one case where premise 1 and premise 2 were true and the conclusion were false, then we would have an invalid row, and the argument as a whole would be invalid. But because that does not occur, this, structurally speaking, is a valid argument. So this is a complete truth table for this argument. Make sure you've written this down before moving on, and try to have a look over it if you're still stumped. Now let's do a little further practice. Really, the way to get good at these truth tables is just simply to practice. So let's try to work on truth tables for some complex statements. If we have this example up here that I've given to you in blue, I would ask that you try to write this truth table out. This reads, either it is both the case that R and S or Q. So first we have to determine our reference tables over here to the left, and then plug in the values for the complex statement. So remember, we have 3 variables here. We have R, we have S, and we have Q. So if these are the reference tables, we have to build them out, which means we have to determine how many lines we need for the reference tables, right? So go back to your formula and determine how many lines before moving on to the values of the sentence. Whoops. Okay, so if you recall, our formula for the number of lines is 2 raised to n, where n equals the number of variables. So in this case, L equals 2 raised to 3, because we have the 3 variables, R, S, and Q. So that means that L equals 8. So we need 8 rows to build out a complete truth table. So to build out the reference tables, we are first going to divide 8 in half in terms of the truth values for our first variable, R. So we have 4 rows that are true under R. True, 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 true. And then 4 rows that are false. False, 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 false. Now we're going to build out the values for S. So we split these in half so that we're going to be working with values of sets of 2, as it were. The first 2 rows of S are true. We always start with true values. 2 true, and then false. False, true, true, false, false. And then we split these in half for Q for our final row, where we're just alternating true, false, true, false. Oops, made a mistake. This is very easy to do. True, false. Now we need, finally, true, false. Okay, so we have our reference tables here to the left, and do make sure these are as tidy as possible with the different rows lining up, because this is what we're sort of plugging in to our values for the sentence. Now we can move over to our sentence, which says either it is both the case that R and S or Q. So remember, in order to do this, we have to think about our main operator, because our main operator is the goal. This is the thing towards which the entire truth table is trending, as it were. So as I see it, our wedge, our disjunction, has to be the main operator, as it is occurring outside of the parenthesis. So wedge is our goal. But unfortunately, we cannot begin with our goal. The goal has to be the last thing we find the truth values for. So we have to begin with the simplest parts of the sentence first and build out to the most complex. So we are first going to work with in parenthesis and try to find the values for dot. So to find the values for the conjunction, we have to think about the truth functional rule for conjunction and apply it to the values of R and S as they appear on the truth table reference column. So remember, what is our rule for conjunction? When is conjunction true and when is it false? Conjunctions are true only when both of the conjuncts are true, only when both of the variables that are brought together with dot are true. As soon as one of the conjuncts is false, conjunction as a whole has a false value. So let's plug in the values for dot by comparing the values of R and S on our truth table. So you could, if you'd like, rewrite the values for R and S, simply copying it in from the reference table in parenthesis, and then running the cross-check for dot. But because things are a little cramped here, I'm just going to write in the values for dot. So on the first row, I see that R, our first conjunct, is true, and S, our second conjunct, is true. So dot on the first row has to be true, because both of the conjuncts are true. Now on the second row, I see that R is true, and S is true again. So on the second row, once again, dot is true. On the third row, I see that R is true, but false under S. So we have a false conjunct. So we know that dot on the third row has to be false. The conjunction as a whole is false because we have one false conjunct. It only takes one. Now on the fourth row, I see that our first conjunct R is true, and once again S is false. So it takes the same value. Dot is false on the fourth row. On the fifth, I see that R is false, our first conjunct, and our second conjunct is true. So dot has to be false because we have one false conjunct, R. Moving on to the next row, I see once again that R is false and S is true. So dot has to be false again. Okay, moving on to the seventh row, I see that R is false and S is false. So dot, in this case on the seventh row, is false. And finally on the eighth row, I see that R is false and S is false again. So dot as a whole, again, on the eighth row, is false. Okay, so these are the values for the conjunction, right? Just trying to kind of indicate that. And it's the conjunction is the outcome in terms of its truth function of the values of R and S. So these are the conjuncts, C1 and C2. All right. So now, in order to find the values for our goal, we have to take as a disjunction the values for dot and the values of q. Remember, the first disjunct is not r and it's not s, it's dot. So the values of dot as a whole form the first disjunction, and the values of q form our second disjunction. Very important to remember what the correct values are when determining the values for the main operator. If we bring the values of r and q together, it's an entirely different analysis, right? So in order to do that, I'm just going to plug in the values of q because I think it's important as a visual aid to have all of them there so that we can apply the values to the main operator. So to do that, I am just looking over to my reference tables and plugging in the values as they appear for q. So q on the first row is true. Q on the second row is false. Q on the third row is true. Q on the fourth row is false. Right, we're alternating now. Q on the fifth row is true. Q on the sixth row is false. Q on the seventh row is true. And Q on the eighth row is false. So we have Q plugged in. Now, last but not least, we find the values for our disjunction, our main operator. So remember, what is the rule for disjunction? The truth functional rule for disjunction is that as soon as we have one true disjunct, the disjunction as a whole is true. You only need one. We don't need two, like we did with conjunction. The threshold for disjunction is much lower because it's an either-or sentence. So let's compare the values for dot, which is our first disjunct, to the values of q. So on the first row, I see that dot is true and q is true. So I know that on the first row, wedge with the disjunction has to be true, right? Both of our disjuncts are true. On the second row, I see that dot is true and q is false. So because I had that one true disjunct, I know that wedge is true again. On the third row, I see that dot is false and q is true. So once again, on the third row, the disjunction is true. On the fourth row, I see that dot is false and q is false. So the wedge must be false as a whole because I have two false disjuncts. That is an instance where we have a false value for wedge. On the fifth row, I see that dot is false and q is true. So now wedge is true again. On the sixth row, I see that dot is false and q is false. So wedge as a whole is false. On the seventh row, I see that dot is false and q is true. So wedge is true. And then in the eighth row, I see that dot is false and q is false. So wedge on the eighth row has to be false. Okay, so these are the values for our main operator, and we've arrived at our goal. So we are going to just put a box around the main operator to indicate, to highlight that this is sort of the most important set of values. It is impacted by the values of every other part of the sentence. And it sort of has as its scope the largest component range of values. So these are the main operator values. Okay. So this is a complete truth table. All right. So make sure you've written this all down before moving along. Okay, let's do another example. Let's write a truth table for this sentence, a little bit more complex, possibly. This says both S and, if not Q, then R. So we have three variables, so we know we need 8 lines on our reference table. We have a couple of different connectives. We see a conjunction, we see a negation, and we see a conditional. So we have to think about what the main operator is. To me, the main operator has to be dot, right? So dot is going to be our goal. But that means it's the last value we're going to try to find. And so in order to build this out, we start with our reference tables where we find the values, or we arrange in columns the values for S, for Q, and for R. So we're going to write out those reference tables, and then we'll be prepared to plug them in to the sentence. So remember, when we are dealing with any sentence, any complex sentence that has 3 variables, we need 8 lines. And so in order to find the values, we divide 8 in 2, and where we begin with 4 true values and then add 4 false values. So S on the first row is true, second is true, third true, fourth true. Now in the 5th row, S is true. On the 6th row, S is true. False for the 5th and the 6th. On the 7th row, S is false. And on the 8th row, S is false. 4 and 4. Now for Q, we split that in half. So we're going to be rotating 2 and 2. We begin with 2 values for true. Q is true on the first row and true on the second. And Q is false on the 3rd and 4th rows. And Q is true on the 5th and 6th rows. And Q is false on the 7th and 8th rows. Now we divide that and we rotate for R, 1 and 1. So R is true on the first row and false on the second. True, false, true, false, true, and in the 8th row, false. Okay, so these are our reference columns. We are just simply going to be using them to guide us as we plug in the values for the sentence. Essentially, it's just every possible combination of truth value for 3 variables. Okay, so now let's have a look at our sentence. I'm going to try to move over here. So we have our main operator outside of parenthesis. So let's work with the simpler part of the expression of the sentence first. Let's plug in the values for our first conjunct. Conjunct 1 is S. So I'm just going to refer back to the values for S on our reference table. So the first row is true. The second is true. The third is true. The fourth is true. 5th row is false. 6th is false. 7th is false. And 8th is false. Okay, so we have the values for S plugged in. Now let's work on the part of the sentence that's appearing in parenthesis. This reads, if not Q, then R. So the most important operator, the most important connective within parenthesis is horseshoe, right? This is bringing together this as an antecedent and this as a consequent. So we need to find first the values for not Q, which is the antecedent. So to do that, we are simply going to look over to our reference columns for Q and negate those values, right? So whatever our values are for Q, we flip them, we negate them. So in the first row, Q is true, so not Q is going to be false. Then I look on the second row and Q is true, so not Q is false again. On the third row, Q is false, so not Q has to be true. And on the fourth row, Q is false, so not Q has to be true. Now in the sixth row, Q is true, so not Q has to be false. And Q is true, so not Q has to be false. On the seventh row, Q is false, so not Q is true. And on the eighth row, Q is false, so not Q is true. So we just have completely negated values for Q under not Q. Now we have the values for R, our consequent, right? We have to find those. And even though they appear right here on our reference table, I think it is useful to rewrite them so that we have a complete table here in order to sort of make sure we're not skipping any steps. So let's just plug in quickly the values for R as they appear on the reference table. And we don't have to do anything to them because they're not negated, they're not modified by any other operator, they're just the consequent. So in the first row, R is true. And then we're alternating, right? So on the second, R is false. And then on the third, R is true. And on the fourth, R is false. On the fifth, R is true. And then on the sixth, R is false. On the seventh, R is true. And on the eighth, R is false. Okay? Now let's find the values for horseshoe, the conditional, right? This is the most important operator within parentheses. And we have to recall our rule for the conditional. Horseshoe, or the conditional, is only false if we have a true antecedent and a false consequent. So every other instance of the conditional will be true. So on the first row, not Q is false, and R is true. So horseshoe on the first row is true. Right? It doesn't matter that we have a false antecedent. The only way horseshoe is false is if the antecedent is true and the consequent is false. On the second row, not Q is false, and R is false. So the conditional on the second row is true. Remember, this is a little counterintuitive. You can have two false values for the antecedent and the consequent and still have a true conditional, right? We're just looking for that instance of a true antecedent and a false consequent. On the third row, not Q is true and R is true. So horseshoe is true. And then on the fourth row, I see that not Q is true and R is false. So here we have a false value, a true antecedent and a false consequent. Okay? On the fifth row, not Q is false and R is true. So the conditional is true. And then on the sixth row, not Q is false and R is false. So the conditional is true again. Then on the seventh row, I see that not Q is true and R is true. So the conditional is true. Then in the last row, I see that not Q is true and the R is false. The consequent is false. So the value is false. We have another instance where horseshoe has to be false with a true antecedent and a false consequent. Okay, so these are the values of horseshoe. Let's just be very clear about that. And the values of horseshoe themselves form the second conjunct, right? So it's not the values of not Q and not the values of R, but rather the values of horseshoe, the conditional, that constitute the second conjunct that are being conjoined by dot. So now we're trying to find the values of dot by comparing the values of the first conjunct, S, to the values of horseshoe. Be very careful about that. Not the values of not Q and not the values of R, but rather the values of the conditional. So remember our rule for the conjunction. Conjunctions are true only when both of the conjuncts are true. As soon as we have a false conjunct, the conjunction as a whole is false. So let's use our truth functional rule to discover the values of dot. On the first row, I see that the first conjunct S is true, and horseshoe is also true. So the first row for dot is true. Two true conjuncts. On the second row, I see that S is true, and I see that horseshoe is also true again. So on the second row, dot is true again. On the third row, I see that S is true, and I see that horseshoe is true. So the third row is true for dot. Okay, on the fourth row, I see that S is true, but I see that horseshoe is false. So we have one false conjunct, so this has to be a false row. Dot is false on the fourth row. On the fifth row, I see that S is false and horseshoe is true, so the dot has to be false because we have this first false value. This first conjunct is false. On the sixth row, I see that S is false and horseshoe is true, so the row has to be false. Dot is false on the sixth row because of this false S. On the seventh row, S is false and horseshoe is true, so dot is false again. This false value is a false conjunct. On the eighth row, I see once again that S is false and horseshoe is also false, so dot has to be false on the eighth row. Okay, so these are the rows, these are the values for our goal, for our main operator. So let's put a box around it to highlight it. And just try to kind of keep this tidy so it's easy to see. And once we have that, we're there. We have the values for our main operator. Dot is true, 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 false, 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 or false. Okay, this is a complete truth table for this sentence. Both S and if not Q, then R. Okay, make sure you have written this one down before moving on. Now let's have a look at this sentence. This reads, it is not the case that if P, then either Q or R. So let's try to write a truth table for this one. Again, repetition and practice is the only way to really get this down. So first we need our reference tables here to the left. So we need the values for P, Q, and R. And because this is another sentence with three variables, P, Q, and R, we know we need 8 lines. L equals 2 raised to 3. So we're going to begin with 4 values for P, true values. P is true, true, and on the 4th row, true, and then on the 5th row, false, 6th row, false, 7th row, false, and the 8th row, false. Now we write out the reference table for Q, and we're alternating in 2s. Q is true on the 1st and 2nd rows, false on the 3rd and 4th rows, true on the 5th and 6th rows, and false on the 7th and 8th rows. Now we write the values for R. We're just rotating true and false. True, false. True, false. Okay. So we have our reference tables here. Now let's try to find the truth values for this whole sentence. So remember, what's our first question? Our first question is, what's the main operator? What's the operator that is has as its scope the widest range of statements? And to me, it's got to be the tilde. The tilde or the negation is a negation of everything that follows it in brackets. So tilde has to be the main operator. So it's our goal. And if it's our goal, the order of operations tells us that it has to be the last value that we discover. All right, so we have to work within the brackets and parentheses first. So let's consider, first of all, the simplest part of the expression, which is the parenthesis, which is a disjunction of P and R. This part of the sentence says either Q or R. I misspoke there. It's either Q or R, right? So let's find the values for the wedge. In order to do that, we are going to use the truth function rule for the values for P and Q as they appear in the reference column. So what we do is recall that disjunctions are only false when both of the disjuncts are false, right? So this is our first disjunct, Q, D1, and this is our second disjunct, R, D2. So in order to find the values for disjunction, we just compare the values of disjunct 1 to disjunct 2 to see if we can generate instances where they're both false. So on the first row, I see that Q is true here, and R is true. So because we have two true disjuncts, the disjunction on the first row has to be true. On the second row, I compare the second values for Q to R, and I see that because we still have one true disjunct, Q, the second row for wedge is also true. We need two false ones for it to be false. On the third row, I see that Q is false and R is true, so the third row for wedge has to be true. On the fifth row, I see that Q is false and R is false. So here we have an instance where the disjunction as a whole is false. We have two false disjuncts. So the fourth row is false. On the fifth row, I see that Q is true and R is true. So the disjunct as a whole is true. On the sixth row, I see that Q is true and R is false. So the disjunct as a whole is true. On the seventh row, I see that Q is false and R is true. So the disjunction is true. And then on the eighth row, I see that Q is false and R is false. So the disjunction on the eighth row has to be false. Two false disjuncts. Okay, so these are the values for wedge, bringing together Q and R. Now let's try to find the value of horseshoe. So horseshoe is bringing together the antecedent P, this is the antecedent, with the consequent wedge. Remember that wedge itself forms the consequent. Not Q, not R, but wedge. Be very careful about that because we have to have the right values plugged in to find the values of horseshoe. So in order to do this, I'm just going to plug in the values for P because this is getting a little hard to see if I don't have that as a basis for comparing the antecedent and the consequent. So if I look over on the reference table, I see that the top row, P, has to be true. And on the second row, P is true. And on the third row, P is true. And on the fourth row, P is true. On the fifth row, P is false. On the sixth row, P is false. On the seventh, false. And on the eighth, P is false. Okay, so now in order to find the values of horseshoe, we are applying the truth function for conditional to the values of P and wedge. So remember, what's our rule for conditional? Conditional is only false if we have a true antecedent and a false consequent. Any other arrangement of values generates a true conditional. Okay, so on the first row, my antecedent is true and my consequent is true. So the first value is true. On the second row, my antecedent is true and my consequent is true again. So horseshoe is true. On the third row, antecedent is true, and again, the consequent is true. So horseshoe, once again, on the third row, is true. Now in the fourth row, antecedent P is true, but the consequent wedge is false. So we know that horseshoe is false on the fourth row. We have a true antecedent and a false consequent. On the fifth row, antecedent is false for P, but the consequent is true. So the value is true for a horseshoe. On the sixth row, antecedent P is false, and the consequent wedge is true. So horseshoe is true. Antecedent P on the seventh row is false, and consequent wedge is true. So horseshoe is true. Antecedent P is false, and consequent wedge is false. So horseshoe is true. Be careful with that. Our inclination is to take two false values and assume it's false, but no. Conditional is still true when we have a false antecedent and a false consequent. Okay, so these are the values for horseshoe. True, 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 false, true, 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 and true. Now, to find the values for our main operator, we are simply going to negate the values of horseshoe. Remember that this is a negation of horseshoe. That is the set of values we have to flip or negate in order to determine the values of the main operator. This is the most important expression or connective in parenthesis, and so it has as its scope the largest number of other statements within it. So the negation can't be a negation of P. It can't be a negation of wedge. It has to be a negation of horseshoe. So in order to do that, we just simply negate these values. So true becomes false. True becomes false on the second row. True becomes false on the third row. False becomes true on the fourth row. True becomes false on the fifth row. True becomes false on the sixth. True becomes false on the seventh. And true becomes false on the eighth. So these are the values for the main operator, and we put a box around them in order to identify them. Okay, so the negation or the main operator is false, 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 true, false, 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 or false. So this is a complete truth table for this sentence. It is not the case that if P, then either Q or R. All right. Make sure you have completely written this one out before moving along. Okay. That is enough for now. In future videos, we will do a little more practice with writing out longer and more complex sentences and finding the validity or invalidity of more complex arguments on the truth table. Thank you, everyone. I will see you next time.